Good afternoon, folks. Hope everybody is doing well. This is going to be our lesson on the science of the 19th century. If you are in my History of Science course, you might want to go onto the Blackboard site and download a copy of this week's handout and lecture notes so that you have some information to follow along with. Now, scope of all this, in the last lesson, we talked a great deal about the biological and geological sciences in the 19th century. And while I will touch on a couple of biology topics today, for the most part, we're going to be hitting the other physical sciences with an emphasis on chemistry and physics for reasons that will become apparent as we go along. Now, it should be understood that the end of the 18th century, beginning of the 19th century, is going to see a dramatic increase in the amount of science being done in the Western world. And that's only going to climb throughout the 19th century. To put this in perspective, in the year 1800, there are approximately 1,000 scientists in the world. By the year 1900, there are going to be approximately 100,000 scientists. A couple of reasons for this. For starters, the scientific disciplines have become fairly mature by this point in time. We are getting a well-established group of scientific fields. The ancient scholasticism is a thing of the past. We are no longer having to debate over whether the ideas of Plato or Aristotle or Ptolemy are correct or how they should be the basis for our thinking, because basically we're now working from more modern bases, including mathematical proofs that allow us to establish definitively that such things as Copernicanism are correct. Secondly, we're going to have largely done away with the mysticism that pervaded throughout the science of the Renaissance and even into the Enlightenment. Astrology has given way to astronomy. Alchemy has given way to chemistry. There's no longer really any room in empirical science for the folding in of magical or mystical doctrines. The standards of proof are now based around the scientific method, and it becomes exceedingly difficult in just about every area of inquiry, save for biological evolution, to really talk about science in terms that are not experimentally and empirically provable. Thirdly, speaking of empirical proof, we have the metric system now and a well-established body of scientific principles. Metric measurements established in France in the late 1700s don't sound like a major accomplishment, but in many ways they're going to lay the foundation for a mathematical grounding of the sciences at a level not previously seen, that we're going to be able to derive equations, mathematical relationships between physical forces at a level unimaginable in any previous era. And that's going to greatly deepen our understanding of chemistry, physics, and any other sciences that rely on their principles, which is to say, all of them. We're also going to find that our toolkit for the investigation of science has grown considerably. The Industrial Revolution has given us a wide range of technologies that make new kinds of experimentation possible. In particular, experiments with both gases and electricity have opened up entirely new doors in chemistry and physics, allowing us to learn about chemical reactions we could not have studied before, allowing us to build experimental apparatus that could not have been made before, powered by electrical forces, and giving us a whole range of toolkits for expanding the list of known chemical elements, which is going to be tremendously important for getting the field of empirical chemistry solidly on its feet and moving forward. And finally, let's talk about there being a greater demand for science. The Industrial Revolution has embedded scientific principles directly in the manufacturing economy, and increasingly both governments and private industries are going to see the utility of sponsoring scientific research, not only for the sake of improving theoretical knowledge, but also for practical benefits. The 19th century is going to see a great explosion of practical, applied scientific research as we endeavor to find ways to use our newly discovered scientific principles to benefit human life and for economic and technological gains. And that's going to include a lot of industries sponsoring their own science. It's no longer exclusively that you need a job in science to be affiliated with academia. It's now feasible for your academic job, for your science job, to be a government position or to be an industrial position, or even funded by private foundations dedicated to research for their own interests. Now, we are going to see a couple of changes in the way that science is going to be done as a result of all this. For starters, science, and note I'm saying science here, not natural philosophy, that term is a thing of the past. Science has become professionalized at this point. We're going to find that scientist is now increasingly a recognized field of study. It's a career. You can go to a college, you can get a degree in sciences now. Now, make no mistake, there are still quite a fair number of people who are going into science with a well-rounded liberal arts education and not with a degree in a specific scientific or mathematical discipline. But increasingly, universities around the Western world are going to have academic departments dedicated to the study of science, separate from those dedicated to areas like philosophy or medicine. And that means that by the end of the 19th century, you were able to get a degree in physics, in chemistry, in biology, or in other named specific disciplines. This is going to lead to a greater credentialing of scientists, which is going to have the effect of meaning that a lot of our gentleman scientists are going to begin to fall by the wayside. We already saw a little bit of that in the late 18th century, where people such as Joseph Priestley were not taken as seriously by their fellow scientists simply because they lacked a formal education or training that included empirical research. Now, there are still going to be gentlemen scientists throughout the 19th century, not a lot of them, however, and less as time goes on. By the time the 20th century rolls around, it's going to be pretty much expected that to be taken seriously as a scientist, you're going to need to have formal academic training in science, usually meaning at least a bachelor's degree, if not a higher level degree. Now, coming with that increased professionalization is also going to come wider awareness of what is going on scientifically. Improved communication technology, both the mass production of documents using industrial-driven machinery, like massive factory-driven printing presses and so forth, as well as long-distance communication technologies facilitated by things like the telegraph and steam-powered vehicles that can travel much faster, mean that scientific knowledge is spreading more quickly and easier to obtain. New discoveries are getting into people's hands more rapidly. There are more ways of doing it. And it also means that they're cheaper and more accessible, which also means a greater number of ordinary people in a world with increasing literacy are aware of what's going on. This is opening doors for folks to get into the sciences from a less than elite background. There have been a few scientists who came from the lower classes that we've mentioned here, but not a whole lot of them. But throughout the 19th and into the 20th century, it's going to become increasingly possible for folks with an interest in the sciences who can manage to find their way into the halls of education to make a go of it as scientists, even if their beginnings were comparatively humble. This means a wider diversity of minds, wider diversity of ideas, and a certain amount of competition that's going to be healthy for the pursuit of new ideas. Wider publication and wider awareness of the major problems in science also means that this growing number of scientists with growing numbers of careers are all pretty well aware of the major problems in their disciplines, which means that any given scientific issue or problem is likely being worked on by several people at a time. As such, it sometimes becomes difficult for us as science historians to definitively say, here is the person who discovered this thing. Sometimes because several people got to the discovery at right about the same time, and the person we remember for it often ends up being whoever published first or whoever published best, or in some cases, whoever's particular form of that discovery was most dramatic or flamboyant. It also becomes difficult because, for the most part, scientists are not solitary geniuses anymore. Throughout the 19th century, more and more research is going to be done by teams of people, by scientists who are working with others, whether it's students or whether it's collaborating with other scholars on joint endeavors, especially in the halls of academia. I'm going to mention a lot of specific names today, but a lot of those names are going to be the names of people who were the heads of research teams or the solitary geniuses still plugging away at their own discoveries. There which we still have in the 19th century, we still have today, but for the most part, science is increasingly becoming a team endeavor. Now, all of this means that there's much more support for scientific research, both private and public. There are a lot more ways to make a living as a scientist. There are a lot more careers in science. There's a greater degree of access to scientific knowledge. There are many more scientific societies and organizations, both private and government sponsored, and there are many more scientific publications, including a wide range of journals dedicated to specific scientific disciplines, some of which, such as Nature and The Lancet, are still in print today. Now, this explosion of new knowledge, however, does mean a couple of things. It means, first off, that you're seeing fewer and fewer polymaths. Thomas Young, whom we talked about a couple lessons ago, is one of the last true polymath scholars. The simple fact of the matter is there is now so much scientific knowledge available that it becomes increasingly difficult to be a master of more than one discipline. And as a result, you're going to find a lot more specialists, people who, rather than doing a very wide range of things, might be good at one or two things. A physician who also does some chemistry, for example, because those are related disciplines. A physicist who does some astronomy, that sort of thing. But more often, you're going to say, all right, this dude's a chemist. This person is an electrician. This person is a biologist. This person is a paleontologist. We're going to have more and more subspecialties developing, and it's becoming increasingly common to be a specialist in a particular aspect of a discipline, not just even in one singular discipline. And rare are the individuals who can master maybe more than two disciplines. We're also going to see, however, that in addition to this siloing of knowledge, that we're going to have fewer and fewer opportunities to really break from orthodoxy. An ironic thing about this new era of widespread science is that well-known ideas are starting to become entrenched. And science is going to be starting to build something that we took some pains to demolish during the Renaissance and the Enlightenment. Namely, we're starting to build a corpus of authority, where we're starting to say, oh yeah, well, this is an idea of a great thinker like Robert Boyle or Isaac Newton or what have you. And that means that it becomes a little harder to challenge established ideas, that you have to fight a little bit more to get your novel ideas accepted when you've got this large scientific establishment that you're pushing back against, including people who professionally might feel well invested in their particular version of the truth at this point in time for professional reasons. We're also going to find that this means there's less room for individual innovation. Well-established methodologies are kind of standards, and people who deviate from those things are going to have to work a bit harder to get their novel ways of doing things accepted, particularly if those things are very, very radical. This is not to say the 19th century is not a time of radical discovery and reinvention. There's a lot of that going on, but it does mean that science is beginning to build a sort of inertia of its own, built in with ideas that are come to be widely accepted and widely experimentally demonstrated. So this is kind of what we're seeing. It's really going to be kind of a golden age for science research in a lot of ways. Many opportunities, many toolkits to do things that we couldn't do before. The work that we talked about in the last couple weeks, the establishment of new principles in cell biology, in physics, in chemistry, is going to in turn provide a jumping off point for a wide range of new ideas. And really the foundations of the science you know today, as you know it today, are going to be built during this time period. You would find that the science done in the 19th century is recognizable as compared to the science that you do in your labs today. Now, the 19th century is going to see improvements in all areas of scientific discipline and the appearance of entirely new disciplines and subdisciplines, particularly involving rarefied fields that we couldn't study before, like electromagnetism and thermodynamics. I'm going to be focusing in this lesson primarily on the crunchy physical sciences, if you will. A lot of this is going to be about chemistry and physics, because they are really going to grow and expand during this time. Biology and geology we talked about in detail in my lesson on the Darwinian Revolution. If you've not already taken that in, you should. And we're going to hit on them a little bit, but not as much. We're going to mostly be focused on the core physical sciences and their innovations. They're going to feed upon one another. New discoveries in physics are going to enable new discoveries in chemistry, and vice versa. The new industrial technologies of the age are going to help every discipline along. And although there's increasing specialization, there's also a lot of cross-pollination of ideas, in which new discoveries in physics lead to new discoveries in chemistry, which in turn lead to new discoveries in biology and medicine. So there's going to be a lot of this woven together. All right, so where I'm going to begin, having just established all this about the professionalization of science. Let's start our story today with a fellow who is not a professional scientist, one of the last true amateur scientists who really makes a big splash. You might have noticed a name from a chemistry class in the past, an Englishman by the name of John Dalton. Dalton was born in 1766, dies in 1844. He is a chemist, physicist, and meteorologist, although he doesn't often get a lot of credit for that last one. And you might know him as the father of modern atomic theory. Dalton was a quiet and unassuming man. He was a Quaker, very peaceful, very kindly sort of fellow. Had no formal education, never attended college, had no wife, no children, largely kept to himself. Did not even have a lot of close friends. Dalton's private life is little known even to contemporary biographers. We know that he worked as a village math teacher, but he was quite interested in the developments of science, kept himself well educated in scientific research, kept up with the latest developments, and began doing private experiments for his own edification. He gained a reputation locally as a fellow who had some knowledge of the sciences, and began giving science lectures on the side to earn some extra money. Being a village math teacher is not a terribly well-paying profession. His reputation as a well-educated scientific scholar began to grow, and eventually he was appointed the professor of mathematics and natural philosophy, as it was still called at this institution, at New College in Manchester, England. A position he held for a number of years, but eventually quit to become a private tutor because he felt that suited his talents better. Dalton experimented with a wide range of things, largely related to the basic physical sciences of chemistry and physics, but he touched on several different areas. Dalton was colorblind. He was quite fascinated by the phenomenon of color vision. He endeavored to experiment with physics to try to find out why color vision happened. He's the first person to write a formal description of the phenomenon of color blindness, which is still to this day in England sometimes called Daltonism after him. Although he mistakenly attributed color blindness to the discoloration of liquids inside of the eyeball. He was quite interested in meteorology as well. He's one of the first empirical meteorologists to do serious long-term meteorological research. Dalton kept a daily weather journal for a period of 57 years, which began the practice that is now common in meteorology of keeping long-standing weather records for future reference. Now, as Dalton is experimenting with wet meteorology, you can't play with meteorology for long without learning a few things along the way about air pressure. And so he becomes interested in pneumatic science, the behavior of gases. He constructs a pump and begins doing his own researches on mixed gases by the early 19th century. By 1801, he had conceived what is now known as Dalton's law of partial pressure, the idea that the total pressure that gases exert on a container they're in is the sum of each of their individual pressures that each would exert on its own under the same conditions. Now, Dalton's law of partial pressure got him interested in the nature of gas. What exactly was it like? And he reasoned quite accurately that if you can pump more gas into a fixed container, and that the pressure within that container grows, in accordance with principles of Newtonian physics, the only way that's going to happen is if there are more particles colliding with the inside of the container. That the only way you can get increased force in that container is if something is exerting that force. And Dalton surmises that if I keep on pumping more and more and more gas into my fixed container, and the pressure is growing and growing and growing, the only possible way that can be is if there are more units of gas colliding with the inside walls of that container. And on that basis, Dalton concludes that gas must be made of discrete individual particles rather than a single continuous medium. On that basis, Dalton begins his investigations of what the ancients, back to Democritus, knew as atomism. And in 1808, he publishes a text called A New System of Chemical Philosophy, in which he introduces the foundations of modern atomic theory. He lays out a table of the estimated atomic weights of all elements known at his time on the basis of his experiments, and puts together a 5-point model of the atom. Firstly, elements are made up of tiny particles known as atoms, establishing the atom as the basic unit of every chemical element. Secondly, all atoms of a given element are identical. We, of course, realize he was wrong about that now. Dalton did not know anything about isotopes, which will be discovered approximately 100 years later by J.J. Thomson and Margaret Todd. Thirdly, atoms of a given element differ from those of every other element. That, of course, is true. Fourthly, atoms of one element can combine with those of another element to form what Dalton called compound atoms, which today, of course, we just call compounds. He never actually realized that atoms of the same element could combine to make larger molecules of that element, nor did he realize that you can have differing numbers of atoms of the same type in a molecule. For example, Dalton's formula for water would have been HO. And finally, Dalton found that atoms cannot be created, divided, or destroyed by any known chemical means. Of course, today we know that can be split by nuclear means, but the basic foundation that an atom cannot be chemically broken down is considered still valid today. Now, Dalton's ideas were not widely accepted right away, partly because he was dusting off an ancient classical theory in the modern era and took a little bit of a push to get that acknowledged, partly because of philosophical objections to the idea of atomism, which a lot of scholars are still pushing back against, partly because in an era of experimentation, a lack of empirical proof of the existence of discrete particles of matter in this way is lacking. And also partly, frankly, because he's not taken seriously as an amateur. A lot of other scientists point out flaws in Dalton's research methodologies and therefore conclude that his ideas must also inherently be flawed. Now, throughout the 19th century, little by little, growing bodies of evidence in chemistry are making it more and more apparent that Dalton's ideas are, in fact, correct. By the time he is in his twilight years, atomism is beginning to catch on. By the 1850s, it is largely accepted as a basic principle in chemistry, although definitive proof of the existence of atoms will not be found until Albert Einstein is going to offer it in the early 1900s. Now, honestly, that was Dalton's last big contribution. Atomism is a big one, but he didn't really do a lot of very significant science after that. He devoted most of his remaining years to his private experimentation. He was held back in this regard by the fact that he rejected a lot of the experimental models of his contemporaries and the more accurate atomic weights put forward by better trained scientists after himself. He also rejected the use of atomic symbols proposed by later chemists, and basically he was held back by a refusal to accept a lot of the chemical ideas that people, frankly, with better training than himself were putting forward. Dalton had a series of paralytic strokes throughout the last 6 years of his life, finally succumbed to his third such stroke in 1844. At his request, his eyeballs were donated to science in an effort to try to understand why he was colorblind. They were actually formally studied in 1905, and it was found that he actually had a very unusual form of colorblindness called deuteroanopia, whereas the more modern form of colorblindness, red-green colorblindness, is deuteroanomaly. So a little postscript to his story there. Dalton's eyeballs are still stored at New College. All right, so Dalton's atavism is going to be an important foundational principle. While it's not accepted right away, a lot of people are going to see some validity here and are going to work very hard to demonstrate these principles and see what we can learn from them. And as the 19th century wears on, more and more scholars are going to begin to see basic truths in atavism. One of those folks is a French chemist and contemporary of Dalton's. You might have heard of him in your chem class at some point by the name of Joseph Louis Gay-Lussac, Gay-Lussac. Gay-Lussac was born in 1778, died in 1850, chemist and physicist, educated at home, spent much of his life as a professor of chemistry and physics, teaching at various institutions throughout France, although he left academia eventually to serve as a parliamentarian in the French Chamber of Peers. Gay-Lussac was kind of a playboy scientist. He was this larger-than-life figure who did these big, grand experiments. He was known as kind of an adventurer, very flamboyant kind of science in the public eye. He was noted as an aeronaut, and if you don't know that term, A-E-R-O-N-A-U-T, that was a term used for the adventurous souls who went up in the first flying machines. I'm referring, of course, to hot air balloons, which the discovery of hydrogen made possible. You could then fill up a silk balloon with hydrogen gas and cause it to lift a basket containing a person above the ground. So hot air balloons were the first flying machines, and the people who piloted them were aeronauts. Gay-Lussac was a noted aeronaut. He went up in hot air balloons throughout the 19th century, flew over France to great acclaim. In 1804, he took a barometer with him up into his hot air balloon in order to note changes in air pressure. He noted that as you climbed in altitude, atmospheric pressure decreased, leading him to the conclusion that there must be an edge to the atmosphere beyond which you would find no more gases, and there would be potentially a vacuum in space. He realized, however, with further experimentation, that although the pressure of the atmosphere changed with increased altitude, the basic composition of it did not, that the mix of gases was uniform throughout the atmosphere. Gay-Lussac's gas research led him to do experiments on the ground as well. In 1809, he realized that gases can combine in proportions by volume, noting specifically that if you combined 2 volumes of hydrogen with 1 volume of oxygen, you would get a single unit of water, that you needed a 2-to-1 ratio of hydrogen and oxygen to make water, H2O rather than HO. And that was a very important discovery in chemistry, realizing combining elements in different proportions will give you different outcomes. He was also involved in more hands-on sorts of chemistry. Gay-Lussac corresponded and worked with a couple of other noted chemists of his day, the Englishman Sir Humphrey Davy and his French colleague Louis-Jacques Thénard. Together with these fellows, he co-discovered the element boron in 1808, and in 1811, he individually discovered iodine. He'd also devised a number of important tools used by chemistry today, including many things you've no doubt employed in chemistry labs yourself, such as the burette and the pipette. So Gay-Lussac's making some important contributions. We're starting to build a story of, how elements combine. And those of you who are chemistry folks have probably noted an important pattern that I just mentioned and kind of glossed over. Combining elements not by atom, but by volume. Volume of hydrogen and equal volume of oxygen. That tells us an important truth about those volumes of gases at a given temperature value. And so people are going to start poking at this. And one of those people is a fellow with a mouthful of a name, Lorenzo Romano Amadeo Carlo Avogadro, the Count of Quarenga and Cerreto. Avogadro, A-V-O-G-A-D-R-O. You've almost certainly heard that name in a chemistry class. Lorenzo Avogadro is usually what we call him. Born in 1776, dies in 1856. Avogadro is an Italian chemist. He is born to a noble family in Turin, studies ecclesiastical law, but never goes into a church life. He instead finds he's much more engaged in physics, eventually becomes a professor of physics at the University of Turin. Ends up losing that chair eventually because he becomes quixotically engaged in an odd political cause, namely Sardinian nationalism, the island of Sardinia attempting to break away from the control of other Italian kingdoms. And I say Italian kingdoms because there's not yet one unified Italy in this time. His advocacy for Sardinian independence ends up getting him in some political trouble, and he loses his academic posting. But that's really about the most notable detail of his biography. We're more interested in his contributions, of course, to chemistry and physics. In 1811, Avogadro proposes the idea that equal volumes of any two gases contain the same number of molecules at a given temperature and pressure. That principle, known to some of you as Avogadro's law, is going to be the basis of both atomic molecular theory and of a really important principle in chemistry called molarity. Combining this with Gay-Lussac's discoveries, Avogadro realized that there was a fundamental difference between atoms and molecules, and that elements could come together, that atoms of elements could join up to form molecules. Avogadro called atoms elementary molecules instead. He didn't call them atoms. In the course of this discovery, he also was the first scientist to make the important mathematical distinction of mass versus weight. Avogadro's ideas were not well accepted at first. They were finally confirmed by another Italian scientist by the name of Stanislao Cannizzaro, Cannizzaro, way ahead in 1858. So Avogadro does not live to see the widespread acceptance of his ideas. Now, you might have noted that as I was listing the achievements of a fellow named Avogadro, I didn't mention the one you probably know best, namely a thing called Avogadro's number. I will get back to that. Avogadro did not devise Avogadro's number. It was named in his honor because of his discovery of the most basic principles of Avogadro's law at the foundation of molarity. But that's a little bit further in time. I'm trying to move a little bit chronologically here. Shifting our attention back to England. Let's talk about a very colorful English scientist, a fellow who has the interesting distinction of being one of the last true amateur scientists, as well as one of the first paid professional ones. A guy by the name of Sir Humphrey Davy. Davy was born in 1778, died in 1829, a native of the English region of Cornwall. If he was asked his ethnicity, he would say he was Cornish rather than English. Davy became well known as both a physicist and chemist during his lifetime. Now, Davy was one of these folks we don't hear a lot about up till now that comes from a very humble origin. He is the son of a wood carver, although his father aspires for him to have a more rarefied job, and as a teenager, he is apprenticed to an apothecary. And if you don't know that word, Apothecary. An apothecary is what today we would call a pharmacist. Apothecaries were druggists. They were people who compounded drugs for the consumption of the sick. Some apothecaries worked in partnership with physicians, that a physician would write a prescription and the apothecary would compound the drug. But a great many apothecaries took patients themselves and offered their own prescriptions, that sometimes you would go to the apothecary rather than the physician. Actually, in 19th century England, there's an interesting dichotomy that arises between the apothecary as a profession and the physician as a profession. Where today, of course, we would expect, all right, if you're a doctor, you've got an MD degree. If you're a pharmacist, you probably have a PharmD degree. In these days, both of these things are still largely taught by apprenticeship, but increasingly medicine is coming to be a more and more academic profession. And as a result, physicians are increasingly going to have some degree of college education. Although I should point out that it's not going to be well into the 19th century before the level of education we expect to have a doctor having today is going to become standard. whereas apothecaries continue for the most part to be trained by apprenticeship. This leads to a certain disdain on the part of physicians for pure apothecaries, and increasingly doctors begin learning to compound their own drugs rather than relying on apothecaries to do that for them. One of the consequences of this is that the profession of physician, which is going to be a somewhat more elite profession as time goes on. Some physicians come to be the medical professionals of the well-to-do, whereas the apothecary becomes a medical professional tending to people of lower classes who can't afford the services of a learned physician. And so we have this kind of split in the English medical professions for a while, with apothecaries on one side and physicians on the other. Standardization of medical training is not going to come until the 1900s. And then by that time, we're going to start to really kind of pull this together. And pharmacy is going to be folded into the medical professions. A bit of trivia here. If any of you are fans of Jane Austen, in Jane Austen's novel Emma, one of his characters, Henry Woodhouse, Mr. Woodhouse, is a wealthy Englishman who relies on the services of his family's apothecary as his primary medical practitioner. And you might recall, if you've read Emma, that people are skeptical of that. Like, why are you going to the apothecary for your medical treatment? Why do you trust the apothecary to take care of you when you are sick? Because in Jane Austen's England, the apothecary would have been viewed as a lesser medical professional, and it would therefore an unusual eccentricity of a fellow of Mr. Woodhouse's station that he would rely on one for medical care. This is incidentally because Jane Austen, as herself a young woman, came from a family that relied on an apothecary for medical care and therefore had a great respect for their abilities. But I digress. A little bit of a digression there, but I thought it was an interesting story to tell. But anyhow, though, Davy is apprenticed to an apothecary, and while under his training, begins learning some things about chemistry, because the apothecary's profession naturally is going to overlap considerably with the growing body of chemical knowledge. And increasingly, apothecaries are going to begin applying chemical principles to the compounding of drugs. Davy reads Lavoisier's Elements of Chemistry when he's 19 years old, becomes fascinated with the subject, and that same year writes a paper on the phenomena of heat and light, in which he denies that caloric is the element of heat and that light is an element at all. That paper gets him the attention of a chemist in the city of Bristol, who offers him a job as his assistant. Now, while Davy is working for this chemist, he begins experimenting with gases, and he accidentally synthesizes a large volume of nitrous oxide, which then balloons up, and he inhales a big old cloud of it. Now, if any of you have ever been on nitrous oxide for surgery or dental care, you know what happened next. And after Davy came down from the considerable high, he said, "Whoa, man, what did I just do here?" Began experimenting a little bit more. I say experimenting a little bit more. And Davy discovers the well-known by now psychoactive properties of nitrous oxide. Now, this might have just been a stoner discovery if Davy had not had the brilliant insights, hey, maybe we can use this as a form of anesthesia. Now, anesthesia is a discipline of medicine that is very, very much in its infancy. And in the early 19th century, your anesthetic options are extremely limited. Namely, get real drunk before your surgery, get whacked on the head before your surgery, or bite down real hard on this stick right here. As a result, surgery was an incredibly painful process and incredibly dangerous. A great many surgical patients died from the complications of being operated upon without anesthetic, and it was a horrifically torturous experience to go through in most instances. Davy's discovery of nitrous oxide is going to offer the possibility of pain-free surgery and dentistry. It's going to be famously demonstrated by an American dentist by the name of Horace Wells a number of years later, but Davy really deserves credit as the discoverer of nitrous oxides as the first viable chemical anesthetic. Sadly for Davy, the part of it that's the getting high part becomes a very deeply embedded part of his life. Davy becomes hopelessly addicted to nitrous oxide and continues to inhale it for recreational purposes for the rest of his life. Indeed, as Davy continues his own chemistry research, he gets into the habit of deliberately exposing himself to different gases that he synthesizes in an effort to see if he can get a better and better high. That frequent exposure to toxic gases is almost certainly a contributing factor to his death at a comparatively young age of only 49 years old from multiple organ failure. Now, in the meantime, however, Davy is getting a lot of attention for his chemical discoveries, and he is appointed to a position at the Royal Institute of London, the RI, you might remember that, founded by good old Count Rumford. Davy gets a position at the RI as a lecturer in chemistry. There he writes a book called Researches, Chemical and Philosophical, published in 1800, updated a couple times throughout his life, in which he talks about his various experiments in the chemical sciences. Davy gets quite a reputation at the RI. He is a very gifted speaker, very well articulate, good at putting things in layman's terms that ordinary folks could understand, and therefore a good advocate for the public education mission of the RI. It didn't hurt that Davy was, by all accounts, a really handsome fellow. One newspaper editorial at the time commenting on Davy's lectures mentioned wryly that the young women of London would come to attend Davy's lectures regardless of what he was talking about, or indeed if he was talking at all. But Davy, in the meantime, however, is getting a lot of folks, including a lot of young women, interested in the sciences. Now, part of being at the RI is not just giving public science lectures, it is also doing ongoing research. And Davy continues his experiments with both chemistry and electricity. He isolates both sodium and potassium. He discovers that chlorine is a distinct element. He provides modern definitions of acids and bases, defining bases as substances that interact with acids to form salts and waters. And he realizes that hydrogen, rather than oxygen, is the essential element present in all acids. Lavoisier, you might recall, thought it was oxygen. Davy also does a couple of other little things. He invents the Davy lamp. It's a simple electric lamp, not like Lavoisier. It's a lamp meant to burn gas, with an electric spark to set it off, not what we think of as an electric lamp today. Sadly for Davy, he doesn't really do a lot of serious research after about 1810. Part of this is because of sloppy research methodology. Remember, he is, after all, not a professionally trained scientist. Partly, it's because his fame is going to his head. Davy is becoming caught up in the reputation he has gained as a lecturer and a scientific advocate and a very well-to-do member of society, and gets more involved with the fame and recognition side of things and begins letting his scientific work slack. He realizes that he is lagging in his research, and he appoints an assistant in 1812 to help him out, an assistant whose name you might have heard before, a fellow by the name of Michael Faraday. We're going to talk more about Faraday later on in this lesson. Faraday ends up becoming a very prominent scientist in his own right, one of the greatest scientists of the 19th century, and in the fullness of time takes Davy's place at the RI. In 1820, Davy becomes president of the Royal Society of London, holds that office for a number of years, and this only, of course, increases his dedication to fame and fortune at the expense of his own professional growth. He actually ends up accusing Faraday of plagiarism because Faraday is getting further in experiments than Davy was. And Davy gets jealous of Faraday's successes in areas that he personally had failed at. So much so that he actually leverages his position as president of the Royal to block Faraday's appointment as a fellow of the Royal Society of London in 1824. Ultimately, Davy succumbs to illness resultant from his multiple gas exposures. He ends up getting into a feud, of all things, with John Dalton, Dalton refuses to accept Davy's view that chlorine is a distinct element, and Davy in turn refuses to accept Dalton's atomic theory, and both men end up looking the worse for this. All right, though, but making some headway. And Davy has established really important chemical discoveries. I mean, nitrous oxide in and of itself is an extraordinary medical discovery, but he's also establishing really important chemical principles like acid-base chemistry and learning about some very vital elements like sodium and chlorine. Picking up from here, we're going to have further progress in the chemical sciences by a number of individuals. We're going to have a fellow by the name of William Prout, another Englishman. Prout is born in 1785, dies in 1850. As I say these words, we're just slightly off the anniversary of his death, April 9th. Prout is a physician who studies chemistry on the side. His personal background is of little interest. He does not have a terribly colorful life for me to tell you about, no real biographical details of note, but his chemical research ends up being far more important than his contributions to the medical sciences. Prout discovers that the atomic weight of all elements can be calculated as an integer of hydrogen. That hydrogen, he determines, is the fundamental unit upon which all heavier elements are based. Therefore, he says hydrogen is the fundamental particle. You chemistry people can probably see where we're going with this. And later in the 20th century, when Ernest Rutherford discovers the positively charged particle found in the nucleus of an atom, he names it the proton after William Prout. Now, Prout is also going to be a pioneer in the nascent science of organic chemistry. As a physician, he's very interested in the applications of chemistry to medical research. Prout proposes an idea that bodily secretions are the result of a breakdown of our tissues releasing chemical compounds. He is the first person to isolate hydrochloric acid in gastric juice and realize its importance for digestion. And in the realm of pure organic chemistry, he proposes a chemical division of foods into proteins, carbohydrates, and fats. Now, I should establish a really important thing here, that at this stage of organic chemistry, it is generally considered that the chemical sciences have two basic divisions. There's a general idea that you have organic and inorganic chemistry, and it is believed that those things follow different rules. There is still a lingering element of vitalism in 19th century science. Remember vitalism, the old idea that living things have their own distinct energy of life that's different than electricity or heat or any other force. Obviously, the work of people like Luigi Galvani is showing that that's not correct, at least not for physics, that electricity is the energy of life, if you will. But there's still a lingering belief that the chemistry of life is not like the chemistry of the inorganic world and that it follows its own basic chemical rules. So we're not having a lot of crossover in between organic and inorganic chemistry just yet. But Prout is starting to apply chemical principles to the study of medicinal and biological compounds, and this is going to be a really important starting point for making that jump. Now, chemistry does not get a lot of recognition for his achievements, although he did a great many useful things. Is going to be a Swedish fellow, physician by the name of Jöns Jacob Berzelius, specifically Friherre Jöns Jacob Berzelius. Friherre is a title of nobility, equivalent of a baron. F-R-I-H-E-R-R-E. The name Jöns, J-O-N-S, with two little dots over the O. Jacob, J-A-K-O-B, and Berzelius, B-E-R-Z-E-L-I-U-S. Oh, if I didn't tell you, William Prout is P-R-O-U-T, Prout. Berzelius is born in 1779, dies in 1848. Native of Sweden, studies medicine at the University of Uppsala. He's actually a contemporary towards the end of his life of Carolus Linnaeus. He learns his chemistry from a Swedish chemist by the name of Anders Ekberg, who's the guy who discovered the element tantalum, although he doesn't really have a lot else to his name. Ultimately, despite his training in medicine, he ends up becoming the professor of chemistry and pharmacy, the newly named discipline of pharmacy, the chemical application of drug making, at the Karolinska Institute in Sweden, which remains to this day a prominent scientific research institution. Berzelius is one of the first early adopters of Dalton's principles of atomism, and he does meticulous experiments in order to compile a chart of the known chemical elements and their atomic weights, which by his time has expanded to a list of 40 elements from the initial 33 proposed by Lavoisier, 2 of which turned out to be not real. His list has more accurate numbers than those of either Davy or Dalton, and both of them actually opposed his ideas on the basis of his numbers being better than theirs. Although his work ultimately is supplying evidence that Dalton's atomism is correct. He's getting more accurate results because he is measuring atomic weights not relative to hydrogen as Prout did, but relative to oxygen. And some of you might be able to conceive why that is, because you might realize that the most common isotope of oxygen, oxygen-16, has exactly equal numbers of protons and neutrons. And therefore, using that as a basic integer to calculate the weights of other elements ends up giving you a somewhat more accurate sense of overall atomic weight by taking the neutrons into account. Now, Berzelius is a very prolific chemist. He pioneers the use of electrolysis as a technology to separate elements in chemical compounds. And on that basis, he and his students discover a number of important elements. He'd be famous enough all on his own for the discovery of silicon, obviously vital as a semiconductor to the entire modern computer age. He also is going to discover selenium, thorium, and cerium. Students working under his supervision discover lithium and vanadium. In addition to these basic chemical discoveries, he is going to be the first person to name and make a distinction between organic and inorganic chemistry. He is going to provide the modern definition of protein as a type of chemical substance. And he's going to introduce a lot of important terminology to the chemical sciences. This is a sort of lesser established idea, but he's going to identify a lot of basic ideas in chemistry that are foundational to many of the experiments we do now, and he's going to give names to a lot of these things, including terms that you've all used in your chemistry and bio classes, terms like halogen, polymer, isomer, allotrope, catalysis. All of these are terms and concepts that are a result of Berzelius's research. And arguably the most notable thing he's going to contribute to the terminology of chemistry, I guess more the symbolism of chemistry, is he is going to devise the system of letter-based symbols used to represent elements and compounds. The atomic symbols based on capital letters or capital letters paired with lowercase letters that we use today were originally devised by Berzelius, at least for those elements known in his time. So, chemistry is really rolling along. Carrying on here. First chemist to be born strictly in the 19th century of our discussion is going to be a German by the name of Friedrich Wöhler. W-O-H-L-E-R, 2 little dots over the O. Wöhler is born in 1800, dies in 1882. Like so many of our chemists of this era, his original training is in medicine, but he ends up finding a greater interest in chemistry than he does in the medical disciplines where he learned it. Ends up becoming a professor of chemistry at the University of Göttingen in Germany. Wöhler is a correspondent with Berzelius. He actually deserves co-credit for the discovery of silicon. The two men worked on it together. And like Berzelius, Wöhler is going to be very prolific in the discovery of new chemical elements, particularly metals. And his contributions to the science of metallurgy are extremely significant. A lot of the basic metals we depend upon for industrial purposes today and that you utilize every single day were discovered and isolated by Wöhler. Among them, aluminum, beryllium, nickel, titanium, and the lesser-known metal yttrium, Y-T-T-R-I-U-M, if you don't know that one. In addition to his discoveries of new elements, Wöhler is also going to make some other vital discoveries in molecular chemistry. He demonstrates in 1834 that chemical groups can behave like and replace atoms in chemical reactions, what we call the theory of compound radicals today, the side groups you associate with the construction of so many macromolecules, especially in biology. Now, his biggest contribution is in the realm of organic chemistry. In 1828, Wohler is doing an experiment in which he's heating up crystals of ammonium cyanate. When he does so, he synthesizes something he didn't expect to create. He synthesizes urea. Now, you might be thinking, okay, guy made artificial pee. Way to go. But here's why this matters. Urea was previously only known as an organic byproduct. It was a substance known by 1828, but it was considered part of organic chemistry at a time when organic and inorganic chemistry are still in their own little separate silos. As a consequence of this, here we have an experiment in which we started with an inorganic crystalline compound, and from it we derived an organic chemical. And thus, Wohler comes to the conclusion that the vitalist idea is wrong, that the energy and chemistry of life are the same energy and chemistry of inorganic matter, and therefore tears down the wall between organic and inorganic chemistry and says, nope, living things follow the same chemical rules as the inorganic world. That right there is probably one of the single most important chemical discoveries of the 19th century. And it's one that's not only going to tremendously improve the science of chemistry, it is also going to dramatically improve our understanding of pharmacy and medicine. That we are going to really begin to understand truly the chemical nature of living systems. Biology as a discipline really needed two big things to take off. One of them was microscopy and the development of cell theory. The other one was going to be the development of organic chemistry and the realization that all the rules of inorganic chemistry apply to the organic world too. So as a consequence of Wohler's discovery that there is one set of chemical laws that applies to everything, suddenly the biological sciences and along with them the medical sciences are going to gain a whole new set of tools for learning how things work, whether that means treatment of disease, understanding cellular processes, or a wide range of other applications. In many ways, Wohler, although he's remembered primarily as a chemist, is one of the most important figures in the history of biology. Speaking of biological contribution, towards the end of his life, Wohler undertook a somewhat more quixotic experiment studying meteorites, and he noted that some meteorites contained organic compounds, leading Wohler to the conclusion that life on Earth may have been seeded to our planet by meteoritic strikes elsewhere, an idea that some biologists still adhere to that is called panspermia, P-A-N-S-P-E-R-M-I-A, the idea of an extraterrestrial origin for life on Earth. Although it's not widely accepted today, most of us in the biological sciences do agree that some of the early organic compounds on our planet probably were seeded here as a result of amino acids deposited in meteorites and so forth, although probably not the beginnings of life as we know. All right, so our chemistry is really taking some major strides, and along with it, our biology and our medicine. Now let's come back to a thing that I had left behind earlier. Let's come back to the idea of molarity. And let's discuss another German by the name of Johann Joseph Loschmidt. German rather than Swedish, so we're going to spell this a little differently. Johann, J-O-H-A-N-N, Joseph, J-O-S-E-F, Loschmidt, L-O-S-C-H-M-I-D-T. Loschmidt is born in 1821, dies in 1895, native of Austria, ethnically German. Like several of the people I've talked about, his personal life is not of great interest. I don't really have any fun biographical stories for him, but I would be remiss if I didn't tell you about his contributions to the chemical sciences. In 1861, Loschmidt discovered carbon ring molecules, which any of you who are involved in organic chem know how important that is to the understanding of the chemistry of life. This is an idea independently discovered, incidentally, by another German by the name of August Kerkule, Kerkule, who publishes a paper on it 5 years later. Kerkule, however, is going to go on to expand on the principle and develop an idea of chemical bonds and valency, which is a reason that sometimes he gets noted for the discovery of carbon rings more so than Loschmidt does. The idea of chemical bonding is also independently conceived by a Scottish chemist by the name of Archibald Cooper, who is going to build on the idea of valency. And a fellow named Edward Franklin, an Englishman, is going to discover valency about the same time. You start to see the thing I mentioned earlier today, where it becomes a little hard to sort out who exactly found one of these things. Now, the big thing for which Loschmidt is noted in 1865 is determining the number of molecules found in 1 milliliter of an ideal gas, the Loschmidt number, 2.687 times 10 to the 19th centimeters to the negative third. Now, using this, Loschmidt is going to expand on this to determine the number of molecules of any substance in 1 mole, and discovers that this is a chemical constant, 6.023 times 10 to the 23rd power, which he names in honor of Avogadro, Avogadro's number. Obviously, this is vitally important to our understanding of chemistry. It gives us a mathematical basis for molarity, and it significantly influences the molecular kinetic theory of gases developed later by Ludwig Boltzmann, foundation of the science of thermodynamics. All right, to tie off our chemistry here, last chemist I want to talk to you about today, at least last pure chemist, is going to be a fellow hopefully you heard of before you came to this lesson. A Russian, a Siberian chemist by the name of Dmitry Ivanovich Mendeleev. Dmitry, D-M-I-T-R-I, Ivanovich, I-V-A-N-O-V-I-C-H, Mendeleev, M-E-N-D-E-L-E-E-V. Mendeleev was born in 1834, died in 1907. He is a native of Siberia, the youngest of 17 children. That said, fortunately for him, he was apparently his mama's favorite, and she worked hard to pay for him to get a college education. Mendeleev studied chemistry, specifically chemistry at the University of St. Petersburg, and ended up going on to establish a world-class school of chemistry there, a distinct department of chemistry, one of the first in the world. Now, Mendeleev spends a lot of his life as a professor of chemistry. The discovery for which he is most noted actually comes when he is writing a textbook. Between 1868 and 1870, Mendeleev writes Principles of Chemistry, which is the most influential chemistry textbook since Lavoisier, and remains in use in college curricula all over the world for much of the remainder of the 19th century. Now, as he is putting together this textbook, updating the chemical sciences, he is looking at the list of elements, which by now has grown to 63 known chemical elements, and he's trying to find a better way to organize them for the sake of his students. And he notices a pattern amongst them. He says, hold on a second here. I can group these elements together. Their properties are not random. There are periodic properties that repeat consistently. Mendeleev begins organizing his elements in this way. And in 1869, he formally presents a paper called The Dependence Between the Properties of the Atomic Weights of the Elements, in which he takes the 63 known elements and organizes them in rows by shared properties and columns by atomic weights, putting together the first known periodic table. Now, those of you who are chemistry geeks, yeah, I did not get that wrong. Mendeleev's table is flipped sideways relative to our modern table, where we today organize the rows by atomic weight and the columns by periodic properties. Mendeleev had discovered the principle of periodicity. and along with it, the notion of valence, which is going to become vital to understanding the atomic chemistry of the 20th century. Now, I should point out in all fairness here, Mendeleev is not the only person to do this, and this really illustrates nicely that thing I mentioned a few minutes ago, that lots of people get to the same discovery about the same time. The same idea of periodicity is arrived at about the same time by an English chemist by the name of John Newlands, Newlands, but Newlands' paper is rejected by the journal to which it is submitted. A French mineralogist by the name of Alexandre Bouguer, Beguyer, also discovers the same thing at about the same time, but Bouguyer's paper is poorly written, and in his paper about a periodic table, he neglects to include an actual table, and as such, his work is not taken terribly seriously. And finally, a German chemist by the name of Lothar Meyer, Lothar, Meyer, Meyer, discovers periodicity actually slightly before Mendeleev. However, Lothar Meyer did not do the thing Mendeleev did that cemented his reputation as being the guy who really gets credit for periodicity. And as far as I can tell, by the way, as far as anybody can tell, none of these dudes were aware of each other's work. They were independently arriving at about the same thing at about the same time, building on the principles that the rest of the field had put together, which is not at all unusual. Now, Mendeleev, he presents this table of 63 elements, but there's a little problem. He's got all the elements sorted in nice, neat columns by weight and nice, neat rows by periodic properties, except that there are 3 gaps in his table. Mendeleev has 3 holes, 3 places where the next heaviest element does not fit into the column that properties say it should. They're not following in perfect sequence. There are gaps in the table. And Mendeleev's colleagues say, Dmitri, if your theory is correct, there shouldn't be any holes. The next heaviest element should slot nicely in to the next periodic column. It's a nifty pattern, but it doesn't hold up. And Mendeleev said, okay, folks, I'm going to make a prediction. Every element I've got listed in this table fits properly into the column that it fits into. Yeah, it may not be the next column in line, but it's the next heaviest element, and I put it in the column where it belongs. The reason I have 3 gaps in my table, gentlemen, is because of 3 undiscovered elements. And right here and right now, before they are even discovered, I'm going to tell all of y'all exactly what chemical properties they will have when they are found. Mendeleev staked his career on this extremely bold hypothesis. And that's what got him the attention that Meyer did not get. Because within 10 years of the publication of his periodic table, all 3 of the gaps in Mendeleev's table had been filled in by newly discovered elements with exactly the chemical properties that he said they would have, thus demonstrating the powerful predictive value of his periodic table and the consistency of the pattern in valency demonstrated amongst the chemical elements. Incidentally, the 3 elements that Mendeleev predicted the discovery of were gallium in 1875, scandium in 1879, and germanium in 1886. Okay, I guess that's a little bit more than 10 years. It's about like 15, 16 years after. But you know what I mean. Mendeleev is going to have this be his biggest achievement. He's going to do some research on solutions and on the expansion of liquids in conditions of varying temperatures. He is going to propose the existence of 2 chemical elements lighter than hydrogen, which prove, of course, not to be real. And he spends the last years of his life doing some odd work. He denies the organic origins of oil. He believes that it's generated abiotically within the planet. And he spends the last years of his life working for the Russian government, engaged in a project of using his chemical knowledge to set standards for the production of vodka, which involves Mendeleev bravely and selflessly traveling all over Russia and drinking as many kinds of vodka as he can. All right, so that's a good bit of chemistry. Let's leave off with some pure chemistry for a while. Let's turn our attention to other things. Let's talk talk for a minute about some industrial science. Let's talk a little bit about the industrial application of the sciences. It's the thing I mentioned that bears some attention. But the story I'm about to tell you about industrial application of the sciences is going to involve some very eccentric individuals. Some applied scientists whose views are strange and whose discoveries are a little bit stranger. In particular, I'm going to tell you right now about a fellow who is very much out of step with the science being done in his time and is going to kind of go down in history as a bit of a mad scientist figure. And this is going to be a German chemist by the name of Karl Ludwig von Reichenbach. How's that for a mad scientist name for you? Karl with a K, Ludwig, Ludwig, von Reichenbach, lowercase von, V-O-N, Reichenbach, capital R-E-I-C-H-E-N-B-A-C-H. Actually, we should be really saying he is Freiherr von Reichenbach, the Baron von Reichenbach, F-R-E-I-H-E-R-R, German form of that Swedish Freiherre, same title of Baron. So Karl von Reichenbach, born in 1788, dies in 1869. German chemist and philosopher. He is educated in philosophy at the University of Tübingen, studies chemistry as a matter of personal interest. Von Reichenbach is a colorful figure. He founds a secret society with the goal of establishing a German-speaking paradise breakaway state on a South Pacific tropical island. Ultimately, that ends up getting him imprisoned for several months for secessionist ideas. But he's mostly known for his contributions to industrial science. Von Reichenbach is going to start numerous factories in Germany and establish the first modern metallurgical laboratory, not in a university, but in a factory, for purposes of making improvements in the science of metallurgy for the benefit of industry. Von Reichenbach gets made a baron for his contributions to science and industry. He is considered one of the first applied scientists and one of the first chemists to do large-scale industrial research. He ends up discovering a number of important things, including numerous chemical compounds derived from oil and coal and tar, most notably paraffin, which is the basis of most modern waxes. But von Reichenbach ends up having a very eccentric end to his career. He is titled a baron, and when you become baron, you get a castle. Von Reichenbach retires from active research, at least in industrial science, in 1839, and becomes interested in human neurological disorders, which he begins studying in the private laboratory and scientific library he installs in Castle von Reichenbach. Starting to sound a bit mad scientist to you? You're absolutely right. Because as von Reichenbach is doing his research on human neurology, he comes to the conclusion that the rejection of vitalism is maybe a little premature. Von Reichenbach concludes that there is a special and separate energy powering the human nervous system, distinct from, but related to magnetism, electricity, and heat. Von Reichenbach names this life principle the somewhat dramatic name Odic force, capital O-D-I-C, named for the ancient Norse god Odin. Odic force, to von Reichenbach, is the energy of life generated by all living things. It is the life principle. He says that it is odic force that makes life distinct from non-life and makes the chemistry of living systems work differently than the chemistry of non-living systems. He says that odic force permeates all animals, all plants, and all humans, that it radiates out from our bodies, forming an aura of energy around us, and that it has a light side and a dark side. If you're getting a Star Wars vibe from this, I certainly did. Now, furthermore, von Reichenbach, in his research on odic force, says, well, let's try to capture and isolate it. Let's try to study it and understand it. And he does a series of experiments to try to grasp the nature of odic force. A lot of these experiments are dependent on his belief that certain individuals are sensitive to odic force, people that he calls sensitives, who are able to detect and sense and manipulate odic force. So, von Reichenbach begins traveling around the German countryside, rounding up people who in their communities have a reputation for mystical powers or visionary trances, or what we would think of as psychic abilities. And he brings them to Castle von Reichenbach to study their supposed powers. A disproportionate number of these people, incidentally, are impressionable young women who are being invited by the wealthy industrial baron, come live with me in my castle for the benefit of science. You are an incredibly powerful child with a rare gift, and I wish to cultivate it. Nice way to get women, I guess. Now, anyhow, though, von Reichenbach brings these folks back to his castles for a series of weird experiments involving crystals and magnets, in which he believes that they can use odic force to manipulate magnetic fields. They can channel and concentrate it through crystals. And his young women will spend hours at a time meditating upon crystals, or trying to mentally bend magnetic fields, or lying naked in tubs of water in pitch dark rooms, trying to see if they can see the auras of the odic force. Von Reichenbach claims that these psychic individuals gain the power to control and manipulate odic force, that they can emanate it from their hands, their mouths, and their foreheads, and they can apply it to such things as speaking across long distances, viewing faraway objects clairvoyantly, healing the sick, and even telling the future. Needless to say, von Reichenbach never finds empirical proof of his notion of odic force. But his research inspires the nascent field of hypnotism, also inspires a whole religious movement known as spiritualism, claiming that spiritual energies can be channeled and copied and understood and manipulated by humans for purposes of contact with the dead. Spiritualism ends up being a pushback movement against the increasingly rigid materialistic views of 19th century science. The spiritualist movement becomes a major religious movement in both the United States and Europe. You have a growing interest in spiritual seances, in mediumship, and people who believe that they can channel ghosts and extrude ectoplasmic vapors from their mouths and so forth. And a lot of this is based on von Reichenbach's principles, providing a veneer of scientific respectability to this very mystical set of ideas. I should point out spiritualism is taken quite seriously by a lot of famous people throughout the 19th century. Charles Dickens is quite a advocate for spiritualism. Abraham Lincoln has psychics brought in to hold seances in the White House, and several physicians become quite enamored of spiritualism. Sir Arthur Conan Doyle, the author of the Sherlock Holmes stories, was a physician who was deeply engaged in spiritualism. Alfred Russel Wallace, the co-discoverer of natural selection, becomes deeply devoted to spiritualism in his later years. And Thomas Alva Edison, the inventor of the phonograph and the light bulb. You don't hear a lot about this involving Edison, but he spends a lot of the latter years of his life trying to perfect a machine allowing electrical contact with the dead. So we're going to have this very weird overlapping of science and spirituality that happens in Victorian England and the United States, and a lot of it is inspired by von Reichenbach's research, attempting to scientifically understand what we would know today as psychic phenomena. This is the beginning of the pseudoscientific discipline that is today called parapsychology. And I must report that parapsychological research is still a thing conducted by private research institutions and even in somewhat quirky academic departments of a few big colleges and universities, including, among other things, Berkeley in California. So, odd little sort of side note here, but I thought it bore mentioning, not only because von Reichenbach's story is just wacky and fun, but also because of the impact that it has in our belief in the scientific basis for supposedly psychic and spiritual powers, and the continual belief in those things among some individuals even to the present day. All right, So that is von Reichenbach. I thought he was a good place to tie off the story of vitalism. Obviously, his ideas never gained widespread traction, but clearly they have an influence that is far beyond the sciences themselves. All right, I've been talking for about an hour and 20 minutes now. If you want to take a little bit of a breather at this point, I'm going to do that thing. I'm going to pause this. In part 2 of this lesson, we're going to continue talking about some 19th century science. We're going to talk about some physics. We're going to talk about some computers, and we're going to talk about a little bit of biology and medicine as well. All right, I'll pick this up in part 2. I'll talk to you all soon. Have a good day.